Good afternoon. My name is Kemal Malik. I'm a member of the Board of Management of Bayer, and I'm delighted to have the opportunity of speaking to you today. I'd like to thank the organizers for inviting me. What I want to talk about a little bit is a revolution in the life sciences. I think we're at the cusp of some technology that will fundamentally change the way that medicine and healthcare is delivered over the next years. And why do I say there's a revolution? When I look back at the time that I was a junior doctor, it took people's PhDs 3 years to work out what a protein did in the human body, to characterize a protein, the chemical structure, and what it was about. We can now do that in 7 seconds. Gene therapy was this hope that was going to revolutionize medicine. We were going to use gene therapy to cure genetic diseases. And then in 2002, there was a tragic death in a clinical trial of a patient, and there was an abrupt end to gene therapy. In 2015, the first gene therapy drug was approved. And I guess the biggest change that has happened is the sequencing of the human genome. This was a major undertaking that took place across the world. It cost 3 billion euros, and it took nearly 15 years. Now you can sequence the human genome in 2 hours, and it costs less than $1,000, and that cost continues to fall. So when you think about it, we are truly in a revolution in the life sciences. And that revolution is driven by 2 things. The first is our understanding of the genome, and I've talked a little bit about that. But the second thing is the huge capabilities we now have in data processing. We can analyze large amounts of data very quickly, but more importantly, we can share that data around the world so people can work on it simultaneously. Now, I talked about when I was a junior doctor, and I treated a lot of patients, but very seldom did I cure anyone. Apart from people who had acute infections, you very seldom cured anyone. So you gave people with acute infections antibiotics, but people had had myocardial infarctions, Parkinson's disease, cancer. You treated them, but you never cured them. And I remember speaking to a professor of medicine who I was working with at the time and said, when are we going to start to cure people? And he said, well, maybe one day in the future. Let me talk about why we might be getting a little bit nearer that. And I'm going to talk about 2 technologies which I think are at the cusp of revolutionizing healthcare around the world. The first of these is DNA editing, and the second one is cell therapy. And I'm going to talk about each of these in turn. To start off with, I'll talk about DNA editing. DNA is the fundamental building block of all of us. Our genome is our entire genetic information. And the genome is made up of genes. We've got about 25 to 30,000 genes in our body. And those genes are what make you who you are. They make you different from the other 7 billion people on Earth. But they also make you different from the other 107 billion people who've ever lived on Earth. You are unique, and that's because of your genes. Of course, you may have your grandfather's smile, your mother's eyes, because you inherit your genetic information, but you are unique. Now, as I said, genes are the building block of your genome. And genes make proteins. And proteins are the things that work across the body. They build your bones, they make your intracellular processes work. That's how your body works, with proteins. Now, the code, and I know there's a lot of techie people in the audience, the code that genes write in is DNA. So DNA is the code for genes. And when you get a cell, and you find DNA. It's this coiled up thing. If you stretch it out, it's about 2 meters long, but about 6 microns wide. So it's incredibly complex. Now, those 25 to 30,000 genes code for proteins, and most of the time, it works. Occasionally it doesn't, and it's not a problem. But sometimes it's truly devastating. Conditions like cystic fibrosis, sickle cell anemia, hemophilia are the result of genetic mutations. The code isn't read properly. There's an error in the code. Cancer is a disease of your genome. That insult may be happening because of something you do. If you smoke, you're damaging your genome. If you stay in the sun too long, you run the risk of damaging your genome. So cancer is a disease of the genome. Now, obviously the holy grail is, can we go in and correct those bits that are wrong and replace them with some good bits? And that was the thinking behind gene therapy. You inject a gene with a virus, and hopefully it finds the right place in the body. Hopefully it gets into the cell, and hopefully it works. There's a lot of hopefullys there. And gene therapy, I guess, has had a pretty checkered history over the years. I talked about the tragic case in 2002 of a young boy called Jesse Eisenberger who had a genetic condition, volunteered to be in a clinical trial for gene therapy, and died from an immune reaction. And that led to an abrupt end of gene therapy. It then restarted, and a drug was approved last year called Glybera. There is a new technology that has the possibility of revolutionizing this whole area. And it's in the area of DNA editing. Basically, and you'll hear about it, it's called CRISPR-Cas. If you go into Google, or indeed any other search engine, and type in DNA editing, you'll get thousands of hits. But those hits won't necessarily be from scientific journals. They'll be from the Wall Street Journal, the New York Times, the Times, the Financial Times. Those are the type of journals and newspapers that are writing about this technology because it is so revolutionary. And to explain what it is, think of it like molecular scissors that go to the error in DNA, chop it out, and replace it with good bits of DNA. It's rather like a word processor with find and replace. You find the error, and you replace it. Now, to explain how complicated this is, you all know Hamlet's Shakespeare. Can you imagine 5,000 copies of Hamlet's Shakespeare? And in one of those copies, just one, instead of having the phrase to be or not to be, which we all know, it says to be or to be in Singapore. And you've got to go into that one addition, find the Singapore bit, and correct it so it says to be or not to be. Amazingly sophisticated technology. As I said, this has the possibility of revolutionizing medicine. Conditions like cystic fibrosis, hemophilia, sickle cell anemia can potentially be cured with this technology. It's also got applications in other areas, cancer, for instance. So it has huge applicability. Wonderful, isn't it? Some of you may know of a journal called Wired. I guess you guys are techie guys, you'll have heard of Wired. And they published an article, or an edition even, about DNA editing. And they said no hunger, no pollution, no disease, and the end of life as we know it. There are concerns about this technology. Those concerns are twofold. The first concern, I guess, is a very scientific concern, but very practical. Will you have an effect elsewhere in the body, so-called off-target effects? And as we go into clinical trials, we're going to have to be very cautious. The second concern, I guess, is a little bit more philosophical. Are we playing God by doing this? We're going into the DNA of human beings and altering it. Are we playing God? Well, Every time a physician makes an intervention, it's not in the natural order of things. When we were cavemen and we got sick, we died. Medicine intervenes in that process. So you could say that every time a doctor intervenes, he's playing God, although I know all physicians think they're gods, but I don't think in practice we ever felt we did that. There is another concern. I've talked about its use in disease. You can use this technology in embryos. Now, if you do it in an embryo, that means every cell in that child will have that change. And then in children they produce, you could have that change. So theoretically, we could make people taller, smarter, brighter, more beautiful. Do we really want to do that? I think most of us would agree that's not something we want to do. And so there is a worldwide moratorium on the use of this technology in so-called germ lines in embryos. Why is Bayer interested in this? We recently signed a joint venture with a startup company called CRISPR Therapeutics. We're going to invest $400 million over the course of the next 5 years in this technology, looking at a variety of conditions, including ophthalmology and heart disease. So this is the first technology that I really think is going to fundamentally change the life sciences. I'm now going to talk about the second one, and that's cell therapy. Bayer is often accredited with being the founder of the modern pharmaceutical industry. Bayer's 150 years old. In 1897, one of our scientists, Felix Hoffmann, synthesized aspirin. And aspirin, as you know, is widely used for a multitude of conditions around the world. For the next 80 years after that, all the drugs we used were chemistry-based. They were made in the lab, and they were chemistry-based. In the 1980s, we started using proteins, predominantly from companies like Amgen and Genentech. We are now at the cusp of using living cells as therapy. And that will be the third revolution in the pharmaceutical industry. There are a variety of these cells that can be used. I'm going to talk about one specific one, which is stem cells. That is a stem cell. Stem cells are very unique because they can differentiate into every cell in the human body. So embryos have stem cells, and they become brain cells, they become lungs, heart, liver, kidney. So they are amazing cells. Now, there are different types of stem cells. There are embryonic stem cells, which can differentiate, as I've said, into every cell in the body. Once again, for ethical reasons, particularly in the United States with the whole issue around pro-choice, termination, etc., because stem cells are derived from aborted fetuses, there is a lot of sensitivity about using embryonic stem cells. And so it's been a bit difficult to make progress in this area until what has been another revolution. In 2012, two gentlemen, Shinto Yamanaka and John Gordon, won the Nobel Prize for Medicine for their work. And their hypothesis was, can you take mature cells, skin cells, blood cells, bits of hair, reprogram them to become like they were stem cells again, so-called induced pluripotent stem cells. So you put them back into being stem cells, which could then be injected and differentiated. As I said, they won the Nobel Prize for their work. Their hypothesis, and this is the only complicated slide I'm going to show you, is, first of all, can we generate stem cells? So they started with mouse and then human cells in 2006, 2007, and said, yes, we can generate the stem cells. Then they said, can we make them differentiate? And they found, yes, they could differentiate them. They could return them to being heart cells or brain cells or whatever. And we now have the first clinical trials in practice in Japan to cure blindness, which is extraordinary. Once again, this is incredibly revolutionary. Why is Bayer interested? We've just formed a new company called Blue Rock Therapeutics with Versant, looking at the use of stem cells in heart conditions, amongst some others. But just think of all the opportunities this could have. I put boldness there, and I guess got a bit of a personal interest, but it can be used in a variety of conditions. Strokes, myocardial infarction, muscular dystrophy, ALS, these devastating conditions where we could use stem cells to actually cure people. Just think, someone has a myocardial infarction, a heart attack. A bit of the blood supply to their muscle goes. They end up with scar tissue. There's nothing much you can do for them at the moment other than give them drugs. We could use stem cells to replace that scar tissue with muscle tissue. And that is quite revolutionary. And that work, it'll be going into the clinic, hopefully, from us next year. So, if I met that professor now, what I'd say to him is, you know what? 15, 20 years ago, you told me one day in the future. I would say to you, the future is now. And what I also believe very strongly, and why I was keen to come here, is we do this through collaboration and connectivity. The DNA editing activity we've done with a startup company, CRISPR Therapeutics, which is headquartered in Switzerland. And we've partnered with them, and as I said, we're investing $400 million over the next 5 years. The stem cell endeavor is with Versant, with a variety of academics and startup companies. The solutions to many of the world's problems are going to require collaboration and connectivity. When Bayer was founded 150 years ago, the average life expectancy in the West was 40. The average life expectancy in the West is now 80. We're an aging population, and we have diseases that need treating. And I make the hypothesis that some of these new technologies are going to be truly transformational, but we need all of us working together to come up with these solutions. Thank you very much.